Okay, so we're going to carry on where we left off yesterday, looking at some aromatic chemistry. What I'm just going to do first of all is just remind you of the very last thing we did, because we're going to really base the entire hour on what we did at the end of the last session. So that was the mechanism for the electrophilic aromatic substitution. So if you remember, we had our electrophile. We don't care what it is at the moment. This is just a general mechanism. And we had our aromatic ring, and we recognise that the aromatic ring has this cloud of electron density. So it's got lots of electrons in it, so it can act as a nucleophile. But we also recognise when it does that, it will break the aromaticity, so there has to be a very strong electrophile for this to happen. And we were drawing our aromatic rings with these fixed double bonds. We recognise that they're not fixed, but we're using that to help us to understand the mechanism. So what we said is we can take a pair of electrons out of the ring to react with the electrophile. Okay, so when it does that, we're using this double bond here, which means that either one of these two carbon atoms is going to add the electrophile to it. Doesn't matter which one you choose, you just have to pick one of them in this case. So I've added it to the top. And what that means is the other carbon atom in that double bond is going to be missing an electron. There were two electrons in that double bond that were being shared. One belonged to the carbon at the top, one belonged to the other carbon. When the new bond is being formed between the carbon at the top and the electrophile, it's used both of those electrons. So one of them belonged to the carbon at the top, one of them belonged to the carbon next to it. Therefore, this carbon next to it has got a positive charge. It's lost an electron. From there, we also then said, well, you know, why does this happen? And we recognise that there is a way of stabilising that positive charge. So we can draw these resonance structures. We can move the electron around the ring, so we can take the electrons from this area, form a new double bond here, or move them to neutralise that charge. It moves the charge down to the bottom. Then we can use the electrons from this area, neutralise the charge at the bottom, and move it over to the side. So we recognise that this was the stabilisation, the resonance stabilisation. So when we see this double-headed arrow, what we're saying is that's a resonance. That's kind of, it's almost saying it's like an equilibrium arrow, except this isn't a reaction, it's just a movement of electrons. So it's just saying that these things are effectively all the same. The electrons are moving amongst them. And then finally what we said is that we know that we can regenerate the aromatic nature of our ring if we were to remove one of the hydrogens. So if we were to do a substitution reaction. So what we said is we can take the electrons from this carbon-hydrogen bond, and we can use those electrons to reform the aromatic system, to reform the double bond. And so what we end up with is we've got a substitution. Because remember, although it looks, you might think it's an addition because we've added the electrophile, we've substituted it for a hydrogen. We just haven't drawn those hydrogens in. Okay? So it's a substitution reaction that we're looking for. So what we're now going to do is to take that information, to take that general mechanism, and we're going to apply it to some specific examples. So we're going to start by seeing how would we add halogen. So again, thinking back to your alkenes, you did adding a halogen across a double bond. We're going to look at how do we substitute a halogen into an aromatic ring. We're then going to look at nitro groups, and then we're going to look at sulfonyl groups as well. Okay, so we're going to cover those now. So, addition of a halogen. Let's see if we can get this to work. 10. Black. Right. So what I said is we have to have a very strong electrophile. So when you had your, when you were doing it to alkenes, you were looking at things like, you were looking at Br2, but we're going to start with Cl, okay? So you had Cl2. Now by itself, Cl2 is not a strong enough electrophile to add to an aromatic ring. It might work to an alkene, but not to an aromatic ring. We need something that's a little bit more powerful than that. So the idea that within the Cl-Cl bond you can polarize it as it approaches an area of high electron density doesn't work in this case. It's not strong enough. So what we do is we add what's called a Lewis acid to it. And in that case, this is AlCl3. So AlCl3, aluminium is further down the periodic table, and what it has the ability to accept and donate electrons. It can do both things. Okay, so in this case, it's going to be there to accept a pair of electrons. So we're going to make a very strong electrophile by putting this in. So I'm going to show you that Cl2 plus AlCl3, a Lewis acid, gives you effectively Cl plus. Okay, and what we know is that chlorine atoms are incredibly electronegative. They really wouldn't want to give up their electrons. So you have to add this Lewis acid for that to happen. So what happens is the Lewis acid is the one that then polarizes the molecule. And what we can show is if we take a pair of electrons from the chlorine, they can add to the aluminium in the AlCl3. Okay, and what that gives us is something which looks like this. Okay, and it's got, the aluminium has accepted a pair of electrons, yes? So it's now created a bond with that chlorine, so it's got an extra electron that it didn't have before. Okay, so this gets a negative charge. And the chlorine did have a lone pair of electrons. It's used both of those electrons to form a bond with the aluminium. It's still sharing one of them in that bond, but it's effectively given one away. So the Cl ends up with a positive charge. Okay, and what we can then see, okay, is you have this positively charged chlorine, and so it's the equivalent of saying this is equal to having Cl plus and AlCl3. Okay, because the way I can say it's like that, because you're thinking, well, that the positive chlorine's in the middle, but of course what we can do is we can take the electrons from this bond and give it to that chlorine. So that would make the end chlorine positively charged. Okay, so at the moment we've got the chlorine here, yeah, which has got the positive charge, but what we can do is we can use the electrons from this bond to neutralize that. So it's like having Cl plus AlCl3. Okay. So we can consider when you put in chlorine gas, a Cl2, plus a Lewis acid, in this case AlCl3, we can consider that to give us Cl plus. And what we can then do is we can go back and we can apply that earlier mechanism, because we now know that our E plus is actually Cl plus. And we understand this is how we would make it. So if you see these conditions in a reaction, you can assume that they will give you a source of Cl plus. Okay? So we can now take that and we can put that into our mechanism we had before. So there are two ways we can do it. I'll show you the simple way first, and then I'll show you how we can add what we've just done here into that mechanism. So we start with drawing our ring. Right, let's try that again. So we've got our aromatic ring, and we have our Cl plus. So if we just consider it to be Cl plus, we can just do the same thing we were doing all along. Okay, we can just use the electrons from that ring to form our bond. we've got our positive charge. Now just to, that's kind of a simplification of the process, that's fine. But just to think about what actually would happen if you think about what we've done with our Lewis acid, we can also consider, that it keeps disappearing on me because I touch it, there we go. Right, we can also consider okay, that was what we had as our Lewis acid. Okay, so how does that make Cl+? Well, if we now draw our electrons to that chlorine, we can then take the electrons from this chlorine to there. So we end up with exactly the same thing. And then we also end up with that. Okay, because we've used the electrons to neutralise that positive charge. So the chlorine is no longer positively charged here, but the aluminium still has a negative charge. So at this point we can draw all of those resonance structures. I'm not going to draw them all, but we can move the electrons around the ring to show that the charge can be distributed. And then finally we can say, well, we've got our hydrogen. Okay. So what are we going to do with that? Well, we can obviously say that this here is, if we take these electrons here, we can place them onto the Cl-. So we can take the electrons from the aluminium, yeah, and we can take those and give them all to the chlorine. And then we've got a Cl-, and then what we can see is the Cl- can come and take that proton away. So where before we just said the proton left, the hydrogen left, we can now see that the reaction gives us a way for that to happen. So we can take the hydrogen, use the electrons in the hydrogen to reform, and then we're going to go all the way down here. And we form we've added our electrophile. So the mechanism is the same as the general one. Okay, we add first of all the Cl+. Okay, we add the Cl+. We form the carbocation in the ring. We can then show the resonance in that ring, and then we can say, well, let's remove the hydrogen and reform the aromatic ring, and we've added our chlorine to our aromatic ring. All I'm showing you with this, that's really what I need you to remember. What I'm just showing you is that it's a little bit more complicated than that. You've got to understand, you know, the Lewis acid can work this way in reality, but if you just put down that you show how Cl2 plus AlCl3 gives you Cl+, and then you use Cl+ in this reaction, I will be happy with that. You might not get the full marks, but you'll get close to it. If you want to really show that you understand it, you need to show that you understand that the Lewis acid acts in this way, and you need to show that there is this equilibrium at the end, which gives you the Cl-. Okay, so that's a little bit to digest. So what I would like you guys to do for me is to digest that and have a go yourself. So what I'd like you to do is show addition of bromine to benzene. So this time you're going to use Br2, so bromine gas, and you're going to add, you're also going to have FeBr3. So FeBr3 is a Lewis acid. So it's going to react, it's going to take the place of your AlCl3. So have a go at that. And in this time, I want you to draw the resonance structures. I want you to think about that and show that you know how to do it. Okay?